So good morning or good afternoon, everyone, depending on where you are logged in. Today, we have the pleasure to welcome with us Professor Grae Worster, who is a professor of fluid dynamics in the Department of Applied Mathematics and Theoretical Physics of the University of Cambridge. And today he's going to discuss sea ice and how he sees it or understand it as a professor of fluid dynamics. So Grae, the floor is yours.
Thank you very much, Catherine. It's a pleasure. I would love to be with you all, but it's good to be able to have this opportunity to speak to you over the internet. So I'll just share my screen. Hopefully this works. Oh, now now I have several things open. I can't think which one it is. Let's try this. Yeah, this will do.
All good.
Good. So let's begin. I don't know how many of you are familiar with the idea of sea ice. I've got a photograph of it here on this first slide, and the sea ice I'm going to be talking about is in the foreground of the picture. There's some ice in the background, and that's the end of a glacial ice sheet, a so-called marine ice sheet. And periodically, this ice sheet will break off and form giant icebergs. And it's icebergs that are coming from ice sheets that sank the Titanic. So I'm not going to talk about that ice at all today. I'm talking about this ice in the foreground. This is ice that's formed directly by freezing the ocean. It's rather thin relative to this ice in the background. If it's 1 year old or so, then this sea ice is about 1 meter thick. And special ice-breaking ships with reinforced hulls can plow their way through that. So that's what we're going to be thinking of. So we're going to start with a little video sequence of satellite imagery showing the North Pole in the middle here. We've got the Arctic Basin, which is covered in sea ice. And what you'll start to get the impression of is a sort of breathing in and out as summer goes to winter and back to summer again. And that's quite natural. And then we see as we enter this century, past 2000 or so, that breathing becomes heavier and heavier. And this particular video is going to stop at 2007, which was a record-breaking year for the least amount of sea ice left at the end of September after the summer, 2007. That record was broken so that's 2007 down here. It was broken in 2012. And since then, it's been hovering around here. So 2012 is still holding the record. But the main thing I want you to take away from this slide is that the world, shown in brown, the Earth, has been outperforming, as it were, all the computer models, all the climate models. And so this big array of graphs here, a whole ensemble of different climate models and their prediction for the sea ice extent. And here we see nature diminishing much more rapidly even than climate models are predicting. So there's clearly something more to be understood, some ways in which we should be trying to refine our climate models in order to make climate predictions. And the goal of today's talk is to give you some of the background ideas that go into the mathematical modeling of sea ice to enable it to be described appropriately within climate models. So let's start with just understanding the scale of the problem. Climate models are often made up of different components. You'll have an individual component dealing with the atmosphere, which has a vertical length scale of about 10 kilometers. That's the height to the tropopause and where all our weather happens. And that's bolted together with other models describing the oceans. Different researchers tend to divide between studying the atmosphere or studying the oceans. And the ocean has a vertical scale of about 1 kilometer. And then in the polar regions, like the Arctic basin that we've just been looking at, these two large fluid regions are separated by this very thin layer of sea ice. I'd say the typical sea ice scale is about 1 meter. So many, many orders of magnitude less than, thinner than the atmosphere or the ocean that bound it. And yet it's very, very important. One of the things you'll have taken away from the video and will realize anyway is that snow and ice are white. They are very reflective, and they reflect a lot of solar radiation back into space. And as we get less ice on the Earth, less solar radiation is being reflected back into space, which contributes to global warming. So that's one property. The other property, which is sort of shown schematically with these arrows, is that the sea ice actually acts as a bit of an insulator. We can have a very cold atmosphere, -20, -30 degrees Celsius is quite typical in the Arctic winter. The ocean, even in the Arctic, is sitting at about -2 degrees. But even though the atmosphere is so cold, it's not cooling the ocean very much because of this layer of sea ice. Most of the cooling goes into forming ice rather than cooling the ocean. So we need to understand that interplay between heat fluxes to the atmosphere, heat fluxes from the ocean, and the way that the amount of ice changes in time. So that leads to the first little problem that we might think about modeling. This problem goes back to the 19th century when people were very interested in opening up trade routes, particularly between Europe and the Far East, going over the Arctic basin. Much shorter route than coming down south through the Mediterranean, the Suez Canal into the Indian Ocean, and so on. And so many explorers going out into the Arctic, trying to find passages across the Arctic, and many of them getting stuck in the ice for long periods of time. And so they'd spend their time measuring ice thickness, wondering when they were going to get out. And so there were measurements of ice thickness, and eventually these got deposited at the Austrian Academy, where one Josef Stefan was associated. The same Stefan as in the Stefan-Boltzmann constant you'll be aware of in terms of radiation. And Stefan put together, well, posed, I should say, this mathematical question, which then various people have answered over the decades and since. So the question is how, if I know the surface temperature of the ice, the temperature in contact with the atmosphere, and I know the ocean ice temperature is equal to the freezing temperature, throughout this talk, the freezing temperature is going to be Tm, M for melting. If we were talking about pure water, Tm would be 0 degrees Celsius, the melting temperature of ice or the freezing temperature of water. As we'll see just now, the freezing temperature of the ocean, because it's salty, has a slightly lower freezing temperature of about -2. Anyway, as I said just now, if we take heat out, if we're cooling the surface of the ice because the atmosphere is cold, then there will be heat transferred through the ice to the cold air. And we have a heat flux on the right-hand side of this equation related to the temperature gradient, dt dz, multiplied by K, which is the thermal conductivity. So the conductivity times the temperature gradient gives you a heat flux, which is the rate at which heat is being removed from the system. So what does the removal of the heat do? In this case, the removal of heat is not causing cooling, but it's causing solidification, the change of phase from water into ice. and we can balance that heat flux with the latent heat. This is this L. L is the heat per unit mass required to change water into ice. So we multiply by the density rho, which is the mass per unit volume. So now we've got the heat per unit volume, and then A is the thickness of the ice, which is also the volume per unit area, and the rate of change of that thickness with time. So this is the Stefan equation. We would normally have to solve for the temperature field to put into the right-hand side to determine how rapidly the ice grows. We can do that in an approximate way, actually a very accurate way, as it turns out, for practical purposes, by approximating this temperature field in here with a straight line, as I've indicated, and approximating the heat flux by the slope. So just the difference in temperature between the bottom and the top of the sea ice, Tm minus T0, divided by the thickness, giving us this temperature gradient. So that's, if you like, our first very simple model of sea ice. We can solve it very easily. I've written it again here. There's a lot of clutter in these equations, but most of the clutter are constants. So let's just identify the mathematical structure of this. Our dependent variable is A, our independent variable is T. If I cross multiply by A, then I've got A dA dt is equal to a bunch of constants. And those constants related to the conductivity, the density, the latent heat, and the temperature difference, which we've all seen. And some of those are put together into this diffusivity ratio of the conductivity, the density, and the heat capacity. Anyway, you can probably solve this equation almost in your head. The integral of A dA dt is 1/2 a squared, and the integral of this constant is just the constant times time. So if I sort all that out, I find that the thickness of ice grows in proportion to the square root of time with these constants in front. And you can put typical numbers in that, and we find, as I suggested a little earlier, that the ice grows to about 1 meter thick in 1 year. So far so good. This turns out, although it looks extremely simple, climate models up until very recently were not much more sophisticated than this, and they make reasonable predictions of ice growth. So we ought to look a little bit more carefully. I mentioned the fact that we're growing sea ice not from pure water, but from salty water. And at least we ought to worry about the fact that salt water has a different freezing temperature than pure water. And that's represented here in what's called a phase diagram. Phase diagram is a graph of temperature versus salinity. Here C is the concentration of salt or salinity. And what this shows, it's really a graph of regions. The region above this blue curve is liquid, either seawater, salty water, also called brine. Below the red curve, the system is entirely solid. Down here, that solid consists of ice crystals and salt crystals. Salt crystals like you would have in your salt shaker, you might put on your food. In this region, and you can barely see it, between the black line and the red line, you would get pure solid ice with no salt in it. And we'll see just now that the system doesn't like that state, and it changes rather into sea ice. We'll see precisely what sea ice looks like in just a moment, but I've indicated here that it's really a mixture of solid ice crystals, pure ice crystals, and liquid salt water, liquid brine in between the crystals. So there are two things to take away from this diagram. First of all, the freezing temperature is a function of salinity. That freezing temperature is called the liquidus temperature, and I might use that word as we go through the talk. And the other fact is that the solid that we form, even though we're growing from salty water, The solid part of it is pure ice, has no salt in it at all. So let's watch that happening. We can't see the salt in salt water very easily, so I've used a different impurity. This impurity happens to be clay particles. It could be anything. It could be so any sort of dirt or chemical impurity like salt. And we're going to watch that ice grow. And we say that as the ice grows, if I do this very, very slowly, then the impurity, here the clay particles, but in the context of sea ice, it would be the salt. The impurity is rejected from the ice that is growing, and the ice that forms this blue region, because we've shone a blue light behind it, this ice is completely purified from whatever was contaminating this water. Okay. Now, there's a consequence to that because we've got this layer now of increased salinity, and I'll start calling it salinity. And so the local freezing temperature will be varying through this region because the salinity is varying. And we can plot that up. So what I've plotted schematically here in blue is the local freezing temperature, which is varying with salinity. And it's saltiest at the top, which means the freezing temperature is the lowest at the top. And then as we come down and become relatively fresh, then the freezing temperature increases, and it follows this blue curve. We can superimpose on that a graph of the actual temperature, which I've shown in red. And now you see something very interesting happen. It happens because the diffusivity of salt is much, much smaller than the diffusivity of heat, which means that this impurity doesn't spread as far as the temperature spreads. This is, the temperature is varying on a much larger length scale than the impurity. And in consequence, even though the far field, the ocean, has a temperature red above the freezing temperature, there's this local region where the temperature is below the freezing temperature. So we've created a region here of supercooling, a region of liquid whose temperature is below the freezing temperature. And the system doesn't like that. So I'm going to rush through this slide. We're not going to spend long on it. I just wanted to indicate that you can model this mathematically. So what I've drawn here is the ice-ocean interface. We've got the local temperature field, which I've drawn with a straight line, the local freezing temperature curve, which I've also drawn initially with a straight line. But if we have a corrugation to this interface, then the lines of constant impurity, constant salinity in the ocean are compressed by these peaks and expanded near the troughs. And what that does is allow the impurity to be taken away more efficiently and for this peak to grow. And that leads to an instability. I'm not going to spend time on it. I want to indicate that in general, one can study this mathematically by taking the linear temperature and linear salinity fields and adding to that a small perturbation which is varying sinusoidally, e to the I alpha x, sinusoidally with wave number alpha and a growth rate sigma. I won't go through the rest of the slide, just to say that one can go through the mathematics and find this growth rate, sigma, as a function of the wave number alpha. The wave number is 2 pi divided by the wavelength. So alpha is inversely proportional to wavelength. And I've plotted that result on this schematically on this graph. So this is this growth rate sigma. Remember, we had e to the sigma t. So that's an exponential function of time. If sigma is positive up here, then those perturbations to the interface will grow. They'll grow exponentially. And where sigma is negative, then the perturbations will decay. You'll go back to having a flat interface. And we can just look at this expression and realize that for small alpha, we just have a linear growth, alpha times this function, this grouping, mgc minus g. And so that curve goes up, provided that mgc is greater than g. And mgc, g was the salinity gradient, m is the slope of that liquidus curve, the slope of the freezing temperature curve. So this gives us the slope of the freezing temperature. And if that slope is bigger than the actual temperature, the slope of the actual temperature, then the system is unstable. And this is the same condition that gives you constitutional supercooling that we looked at schematically just now. And so we get instability. What does that look like? Well, if we were growing just a single crystal into a supercooled environment, constitutionally supercooled environment with no surface energy, the surface energy is encapsulated in this parameter gamma, then we would just get fractal behavior. So no longer a planar interface, but something that's fractal. What surface energy does is to stabilize small wavelengths and give some structure to the instability. And it's that competition between a diffusive process, which tends to create lots of anisotropy, very diffuse sort of behavior, and surface tension, which tries to be very regimented, very ordered and structured. And the competition between those two gives you these beautiful branched patterns that one sees in snowflakes, for example. So let me go back to this experiment, and we've seen the video on the left. This had to be done very, very carefully in the laboratory by growing the ice very slowly. If you grow it at more typical rates, typical of what you would find out in the ocean, then we get the video on the right. And you see that we no longer have a planar interface separating ice from water, but we have this so-called mushy layer in which the ice, which is still this dark blue color, forms individual platelets, individual dendrites, and the impurity, instead of having to be pushed ahead of the ice into the ocean, is mostly accommodated in the spaces between those ice crystals. Now, this may seem very complicated to model. This we've essentially already modeled, albeit for a pure water with our simple little heat balance. This looks altogether more complicated, but we make life simpler for ourselves by taking an average over some representative region of this mixed phase material. And that leads us to the idea of a mushy layer. A mushy layer, like sea ice, comprises solid, in this case solid ice, platelets, and very intimate liquid in between the ice crystals. So it has two phases, solid and liquid, has two components. We're thinking about water and salt, and it forms a porous medium, like a sponge. And you may think this is all very exotic, you've never seen it before. I'm very confident in saying that you have all eaten mushy layers in your life, and you know some of their physical properties. So here's probably the most common mushy layer that you've encountered. It's an ice lolly. Ice lollies you pull out of the freezer and you may think they're solid, but they're not. Ice lollies have solid ice crystals, and in between the ice crystals is rather viscous liquid, but it is liquid, a sort of syrup. And you all know this because I bet as children you will have sucked on an ice lolly, and you know you can suck all the nice sugary syrup out of it, which is where all the color is as well. So when you've sucked hard at an ice lolly, what you're left behind with, and I'm sure you can all imagine this, is a sort of fragile matrix of clear, pure ice crystals. And that's the structure of a mushy layer. pure ice crystals, and then all the impurity. In the case of ice lollies, the impurity is sugar and all the colorings in the liquid region between the ice crystals. Okay. Mathematically, we're going to follow mean quantities, but I'll mention that a little bit more later on. So what are the consequences for us, for sea ice? We've essentially still got this picture, and I've given it an elaborate name. People who write climate models and write sea ice components for climate models know this as the zero-layer Sempner model. But it's just a model in which the temperature field is assumed to be a straight line through the sea ice. We have the same heat flux of conductivity times the temperature gradient, balancing the rate of release of latent heat. But you can see two modifications. This sea ice is no longer solid ice. There's a fraction phi of it, which is solid ice, and 1 minus phi of it, which is still brine, still liquid water. So we're only freezing a fraction of this region. Some of it's remaining liquid, and we have to worry about that. We need less latent heat to grow. And also the conductivity is a function of this solid fraction phi. And that's because ice itself is about 5 times more conductive to heat than water. And so we need to worry about the effective conductivity of this material, this two-phase material, as a function of the amount of solid within it. Other than that, we get a very similar prediction as before, that thickness grows like the square root of time, but now this constant in here depends on that solid fraction. So one of the big issues is how do you predict that solid fraction? And until very recently, and by very recently, I mean the last decade, people simply used historical values for phi, taken from ice cores in the Arctic. We know phi is about 95%. And so they stick that into their model and go from there. Okay. So I want to show you some laboratory experiments just to show you what else can happen. We've sort of seen what changes thermodynamically. And what we're seeing here, sped up, is about 6 hours worth of sea ice growth. So we've got some seawater in the tank, salty water in the tank. The top is being held cold, and we're growing ice from the top downwards. And you can already get an impression, I think, that this is not a solid block of ice that you might form in your freezer. This is much more like an ice lolly. You can see some texture. And some of you may have noticed a sort of shimmering in the water below. If we put some tracing paper in front of this tank and shine a light from the back, we can see that that shimmering is a consequence of these streamers of very dense brine, very salty brine, coming out of the sea ice. So I just throw these up. I won't spend time on these equations. I just want to indicate to you that everything I'm showing you today has been modeled mathematically, and these are the sorts of equations that we use. Some of you will be familiar at least with the structure of some of these terms, and so I'll just mention them briefly. The temperature is governed by an advection diffusion equation modified by the internal release of latent heat. Salinity is governed by an advection diffusion equation in principle, but in fact the diffusion of salt is so slow that we ignore it. And on the other hand, there is release of salt, there is injection of salt into the spaces between the ice crystals as the pure ice crystals grow. Okay, so that salt has to go somewhere, and it goes into the interior of this mixed phase mushy region. We insist that the temperature and salinity are sitting on the liquidus curve, so the temperature is equal to the local freezing temperature. And fluid flow, because we're in a porous medium, we have a much simpler description of fluid flow than the full Navier-Stokes equations, and instead describe it by the so-called Darcy equation, which relates velocities to pressure gradients and buoyancy forces. Usual condition of continuity, divergence of U is 0, and a relationship between the salinity and the density. Salt water is denser than fresh water. So those are the sorts of ingredients. I'm not going to talk more about the mathematics, but here are some results. What you can do, similar to the way that we looked at the stability of the planar ice interface, one can look at the stability of this system to convection. So let's just think about what's going on inside this mushy region for a little bit. We're cold at the top, warm at the bottom. Because it's coldest at the top, this is where there will be most ice. And because there's more ice here, more salt has been put into the liquid between the ice. And so the liquid component is saltier and therefore denser up here where it's cold than down here where it's warm. And because we have dense fluid above less dense fluid, they would like to exchange their potential energy. They'd like to turn over like an upright pendulum and create fluid motion, which we see as convection. And that's the origin of those streamers that you saw in the experiments just now. Okay. Some relatively straightforward mathematics using the equations I showed you just now leads to the fact that there will be convection if this very important parameter called a Rayleigh number exceeds a value of pi squared. And you all know that pi squared equals 10, so I'm just going to use the number 10 from now on. Sorry, that's a slight joke. But pi squared between us is close enough to 10 as a rule of thumb. That we will get convection inside sea ice. Convection inside sea ice if the Rayleigh number exceeds a value of about 10. And we see that this Rayleigh number is proportional to the thickness, h, the thickness of the sea ice, and some other parameters. Okay, the permeability, the temperature difference, the viscosity nu, the diffusivity kappa, and so on. But I want to focus on the fact that the Rayleigh number is proportional to the thickness. And let's look at that experimentally. I'll just explain what you're going to see before you see it. We're going to watch a video at the moment. The video isn't turned on yet. The top surface is very cold. It's so cold that we are freezing, we are forming solid ice and solid salt crystals. And that's this whitish region here. Once we're above the solidus temperature, but below the liquidus temperature, we have a mushy region. That's this pale blue region here. This region is the mushy layer. That has solid ice crystals and dense brine in between. Okay, liquid brine in between. When I start this video, you may not initially notice that anything has happened. You won't notice that I've switched it on unless you look at the side. And what you will see at the side is these thermistors, as they happen to be, moving upwards. So what is happening in this is because we're cold at the top, the ice is trying to grow downwards. But at the same time, we're going to move the experimental cell upwards. And therefore, we'll get a steady state. And that's the reason why it won't be apparent to you, if you look here, that I've started the video. So that's the first thing to say. Second thing to say is that in this system where we're holding the freezing rate constant, V is the freezing rate, the thickness of this layer is proportional to the thermal diffusivity divided by the thickness, divided by the freezing rate. So if the freezing rate decreases, the thickness will increase, and you will see that in the video. And remember from the previous slide that if the thickness increases, the Rayleigh number increases, and we should see the onset of convection. So let me start the video and let's see if we can watch that. So the video is now going. You can see that because these thermistors are moving up on the left, but in here you can't see that. We're at a steady state in this moving frame of reference. Now the freezing rate's been decreased and you can see the mushy layer thicken. And when it's thick, you will start to see these much more vigorous plumes coming out from the interface, and they even cause some imperfections to the mushy layer, which I'll show you a bit more. And now we've sped up the freezing rate again, which means the thickness of the mushy layer decreases and the convection stops because the Rayleigh number is now too small. Here's just something that's a bit more visible, because in this experiment, the mushy layer happens to be at the side wall of the tank, and we can see that each of these plumes of dense brine are coming out of channels in the sea ice. So in the context of sea ice, these are called brine channels because brine is coming out of them. And I said everything I'm going to show you has been modeled mathematically. This system, quite complicated, but it can and has been modeled mathematically. I'm not going to say more. Another way of seeing inside sea ice is to use MRI, the sort of thing that doctors use to see inside your body. And using that, these bright colors are where there is liquid, the darker colors is where there's less liquid, and we can see that there are these brine channels formed inside the sea ice. The thing I want to show you here is associated with those brine channels is a decrease in the porosity. This is an increase in the amount of ice. And so because we're increasing the amount of ice, then the amount of space between the ice crystals is reducing. And because the space is reducing, the resistance to flow is increasing. The Rayleigh number is decreasing. So there's a competition here. The Rayleigh number exceeds a certain value which allows convection to happen. Convection causes these brine channels to form, which takes the brine out of the sea ice into the ocean. In consequence, more ocean water has to come in to replace that brine, and that leads to more freezing and a reduction in the porosity, reduction in the amount of water left behind. So we went off to measure this stuff in the Arctic. Here's a picture of my colleagues. We now really are at high up in the Arctic on a place called Svalbard. Here's one of my closest colleague, John Wetlaufer. These are instruments, and a PhD student who is anonymous, Dirk Notz, with his face is out of the picture, holding a lump of sea ice with our instrument embedded in it. And what that instrument was able to do by measuring the conductance was to measure the solid fraction, the fraction of the sea ice that is pure ice rather than brine. And you can see quite a variation. I picked out one of these profiles in red just so you can see it a bit more easily. There is a variation of the solid fraction through at least the lower portions of the sea ice. By measuring temperature, we can also infer the local salinity, and we could put all of that information into determining a Rayleigh number, a local Rayleigh number. So two things are happening while sea ice is growing. The first thing that's happening, which we saw very early on in the talk, is that the thickness H is increasing in time, which causes the Rayleigh number to increase. However, once convection starts, we remove brine from inside the sea ice. We replace it with relatively fresh seawater, which can freeze some more, and that changes the permeability. This capital Pi is the permeability. Think of it as 1 over resistance to flow. It reduces that permeability. So H is getting bigger, and pi, the permeability, is getting smaller. And the net effect is that whereas had there been no convection, the Rayleigh number would have kept on increasing as H increased. The effect of convection is to limit the Rayleigh number to a value close to 10, this critical value. And so we have a self-regulating system, and this is very important in constructing simple models that are computationally cheap enough to put inside a climate model. So, two important messages that I want you to take away in red. Firstly, that sea ice is a mushy layer, and we've understood what a mushy layer is. It's an ice lolly, but made of salt, and that convection in sea ice is self-regulating in an important way that leads to simple parameterization. I won't talk through the other conclusions, really not a conclusion so much as a summary of the things that I've talked about. So I'll stop there, Catherine, and happy to take questions.
Thank you very much for describing to us quite a fascinating convection process in just 1 meter or so.
Well,
So,
I can't see anyone if I'm sharing, so I'm going to stop sharing.
yes,
And if
yes,
there are
yes.
questions and I have to go back, then I'll.
Yes, exactly. So you can, the floor is open for questions. So either you unmute yourself and ask your question, or you can put it in the chat. Any question? Ali.
Yeah, hi. Great. First of all, it's happy to see you after 25 years, when I stayed in Cambridge, it was 25 years ago.
You'll have to remind me where we met. Was that in Damt in Silver Street?
No, actually, we worked together about the 1 year, but not together with John and with Herbert. I worked, but you was next room.
Okay.
It was 25 years ago. Your memory is short than mine. But anyway, thank you very much for the interesting presentation. A few points. First, you several times mentioned that it's a layer increase in the thickness, and that's why it is a Rayleigh number increase. But what about the viscosity? When the thickness increase, how viscosity of this layer changes?
Yeah, not very much if we're talking about seawater. A lot if we're talking about ice lollies.
I see.
And actually, to give a secret away, when I showed you the MRI pictures, that was actually sugar water, not salt water. It's a technicality to do with the fact that MRI machines generally don't like ionic solvents. They can't see through them. But in consequence, the viscosity did change a lot in those experiments, and that had a big influence over the convection and where it happened.
I just thought that it's, but viscosity is decreasing or increasing?
The viscosity increases.
Yeah, that's the point, that it's if there is increase in both sides of the equation, that becomes the Rayleigh number more or less the same. That was my point.
Very much. Goodness me, the viscosity changes by less than a factor of 2. You'd have to get very, very concentrated in brine to double the viscosity. On the other hand, the permeability, which is this resistance associated with the geometry, that will change by a couple of orders of magnitude.
I see. Another point is related to Stefan problem, actually, to the boundary, moving boundary. Did you accounted in this implicitly as an additional term of the heat equation and so on, or you manage this a little somehow differently?
So with the pure Stefan problem,
Yeah.
then you can treat it as an interfacial boundary condition. And that's how all the analysis that I've done has tended to solve it in that way. There are numerical techniques, and I'm thinking particularly of phase field models, for example, which will put that latent heat term into the field equation. So they'll have a phase parameter which varies from, let's say, 1 in the solid to 0 in the liquid over some interfacial scale, which you try to make as small as possible.
Yeah, well,
mimic a sharp interface, but then you just solve a single equation over a single domain, and you can do that.
and at the right-hand side of these equations where you inserted the latent heat release was related to what exactly?
Yeah, so if you were doing pure water turning into pure ice, you would have that same latent heat term,
Yeah.
and phi that I put would be called the phase parameter. So
Okay.
liquid. It's playing the same role in the, and it's sharp. I mean, you're trying to make that interfacial region as narrow as you can, within your numerical scheme. In a mushy layer, you've essentially extended that interfacial region. So the whole mushy layer is where latent heat is being released, not just at the interface.
That's fair.
And then it's very natural for that latent heat term to be just an internal heat source inside your field equation, inside your heat equation.
And another thing which not directly related to these points, which I already mentioned, I just thought that with pressure in the sea, temperature decrease, sometimes even becomes a negative value, very first negatives numbers. And what about the application of this theory in this case? If it is a both side, not warm, I mean, it's because it was a layer below warm, but it's cold.
Okay, so there is a pressure effect. You need about 100 atmospheres to change the freezing temperature by 1 degree Celsius. So on the scale of sea ice, this really is not important. It does turn out to be important for the melting of marine ice sheets. So I mentioned the marine ice sheet coming to the coast, breaking off to form icebergs. But before it's broken off, I'm thinking particularly of Antarctica, there are regions where the bedrock that the ice sheet is flowing over is about 2 kilometers below sea level. And at 2 kilometers, the freezing temperature is depressed by 2 degrees Celsius. And so you can melt the ice sheet at its base because of pressure. And then you form a freshwater plume that travels up the underside of the marine ice sheet. And as it rises up, it depressurizes and it can re-solidify. And then you get something called marine ice, which is really sort of upside down snow, if you like, which starts accreting onto the bottom of your ice shelf. So pressure can be important, but you need to be on quite large vertical length scales.
I see.
Very important for solidification of the Earth's core, for example, which is another example of a mushy layer.
Oh, yeah. Interesting. Thank you. Yeah.
Any other question? There is a comment in the chat. Thank you for the interesting talk. Does thermal buoyancy also have an effect in the development of the instabilities in the mushy layer? Or is it just the moving phase boundary with compositional buoyancy?
Yeah, so 2 things to say. One is I kept things simple today, and I just had the density depending on salinity. It does also depend on temperature. There are two things to say. One is that the salinity has a much stronger effect on density than the temperature. And so to sort of first order of approximation, one can ignore the effect of temperature on the buoyancy. The second thing to say, which is perhaps more important to say, is that inside the mushy layer, the temperature and the salinity are tied to the liquidus. There's this very strong constraint between salinity and temperature. And that means that temperature differences are associated with salinity differences and vice versa. So whereas in a pure liquid, you can have diffusion of heat and diffusion of salt acting independently, which generates lots of interesting fluid mechanical phenomena, inside a mushy layer, they don't act independently, they're acting together, and therefore you can combine their effects on the density and just follow one of those variables. Mathematically speaking, temperature and salinity are the same dependent variable inside a mushy layer.
Let's see. Any other question? Well, maybe thank you to respond the question. Maybe I'll ask one, which is not related really to the model you presented, but actually your first slide, where we see this sea ice broken, like fracture, and it's almost like a patch of the same size, okay?
Very good. Yes. Yeah.
So can you comment on this?
I've had the same observation. So one of the times we were on Svalbard, we were working in fjords, by the way, it made it much easier. So the particular fjord we were at had a thin coating of sea ice. It was about 14 centimeters thick. Now 14 centimeters doesn't sound like it's about this much, you know, it didn't feel like very much. It was thick enough to drive skidoos over. So we were doing that in the evening. The following morning, it was all broken up, like in the foreground that you saw. Now, before it broke up, and we watched this, a very strange sensation. We're standing on the sea ice, or sitting on our skidoos on the sea ice, and you can see the waves from the ocean coming in underneath the sea ice. My speculation is that the size of those blocks, broken up blocks, is related to the wavelength of the waves that caused their breakup.
I see. Has it been modeled or?
No, and one of the things that I sort of thought of at the time, and I've never taken the time to actually model it, is we've seen in the sea ice that really you have platelets of ice. You can almost think of the platelets of ice acting a bit like an accordion, you know, sort of squeeze like this. So now imagine a wave going through. You can imagine it being squeezed like this. Okay. And if you just use lubrication theory for the regions in here, you can get a rectification of that and get expulsion. I should do this upside down. Expulsion of the brine out into the ocean. And of course, what that does is to increase the solid fraction, which will make the ice more brittle. So I think the wave action is a way of making the ice more brittle and then causing it to fracture. Actually, ordinary sea ice, and you can see this in laboratory when it's very thin, is quite sort of plastic on a large scale. Something has to make it brittle for it to crack. This is one mechanism, I think. It hasn't been modeled.
I see. Thank you. Any other question? Comments? No? I think that maybe we'll close it there for today.
Okay.
So thank you again, Grae, because it was really interesting, and I hope my students have enjoyed it as much as I did.
Good. Well,
Um,
it was nice to see you, Catherine. Nice to see you, Alik.
yeah.
Be nice
No,
to
it
see
was
you.
exciting for me to see because I have today just spoke to Herbert Hopper and and then it's attended your seminar. It's just fantastic.
Just like old times.
Yes, exactly.
Okay, so thank you very much. And thank you also for everyone joining us. I think without you participating, we would not continue to do this seminar. So thank you very much for being there. Thank you.